The half-life of a radioactive isotope can be one of the more challenging concepts for a student to master when studying radioactive decay. Not only is it an obvious examinable piece of content, but it's also vital in identifying the correct radioisotope for the correct application in the real world. Radioisotopes have numerous important applications. For example, in medicine, they're used for diagnostic imaging, sterilizing equipment, and in cancer treatment. We need to select the correct isotope for the particular job, taking into account both their half-life and the type of ionizing radiation emitted. In this video, we'll discuss how we can develop our students' understanding of half-life. We'll start by modelling and measuring half-life in ways that students can actively participate. We'll discuss how to ensure that students interpret decay graphs, and then consider useful examples of applications of radioisotopes. Let's start with half-life. Being a physics teacher definitely has its perks, and this is one of them. Here we are modelling radioactive decay using popcorn. Now, one of the key things about radioactive decay that we need to be able to model is its random nature. The fact that we can't predict any time that an individual nucleus to pop. But what we can do, by taking lots of measurements of the decay, is we can work out what is the rate of decay of the body as a whole. So here we have popcorn that can pop at any random time. Now, the difference between popcorn and radioactive decay is that we don't provide any sort of energy to make a nucleus, a radioactive nucleus, decay. Whereas in the popcorn example, obviously we're providing energy. So let's have a look and watch as the popcorn actually decay. So to recap, each popcorn kernel represents one nucleus. Each kernel will pop at a random time. We cannot predict when an individual kernel will pop. This models clearly the random nature of nuclear decay. We cannot predict when an individual nucleus will decay. We could take measurements of the number of kernels popped over time and predict how long it will take for the total kernels to pop, or how long it will take to reduce their number by half, which is the same with a radioactive sample. The big difference between our model and radioactive decay is that with the popcorn we are providing energy to initiate the popping. No energy is transferred to a radioactive nucleus to make it decay. As mentioned in our introduction today, half-life is one of the more complex concepts for students to grasp in the radioactive decay topic, as it appears to be mathematically quite difficult. However, when broken down into simple terms and modelled clearly, students can build a clear picture of how radioactive materials decay. Firstly, let's define half-life. Half-life is the time taken for half of a radioactive nuclei in a sample of material to decay. If we had 1,000 radioactive nuclei in a sample, the half-life would be the time taken for 500 of them to decay. After that same time again, the sample would reduce by half, from 500 to 250, and so on. Radioactive decay, therefore, is an exponential decay relationship. Students need to not only recognise how to read the half-life of a sample from a graph, but also recognise the exponential relationship on a graph. We can model decay in a number of ways, each with their own limitations. First, let's have a look at the skittle model. A sweet like a skittle or an M&M has a marking on one side. Here we can see the S. We will use this to tell us whether or not our sweet nuclei has decayed. Students start by throwing a handful of Skittles onto the desk. They then must identify the sweets that have landed face up and separate them from the rest. These sweets represent the nuclei in our sample that have decayed. Once students have separated the decayed nuclei from the pile, we can get students to consider how many were left and whether this is what they expected. The undecayed nuclei can be taken to be thrown again, whilst the decayed nuclei can be taken to build the first column of their graph. If you're doing this demo with lots of Skittles, then you can pour them into a glass cylinder to represent the shape of each bar. Next, the students roll again and repeat the process of separating out the sweets that land face up. They take these decayed nuclei and build their second bar. Immediately, students can see the difference between the first and second roll. Once again, students throw the remaining nuclei, identify those that have decayed, and add them to the graph. Students repeat the process until they have added all the skittles to the graph. Students can then see the very clear shape that describes the decay of radioactive material. In summary, the skittles can represent the decayed and undecayed nuclei, distinguished by being either face up or face down. After each throw, students can remove the decayed skittles and build their graph. This could be done straight onto graph paper, and for example, students could record the heights of each column to draw conclusions from later. If we do this with more skittles, totaling them up as a class for example, the relationship becomes closer and closer to the true exponential curve. The more skittles in your sample, the closer to a true decay curve you will get. And finally, the limitation of this model is the two-sided nature of a skittle. Each throw gives a skittle a 50% chance of decaying, and as we described earlier, radioactive decay is random. Modelling decay with a two-sided suite will mean that each throw of the skittles will result in one half-life. This could give students misconceptions about time and half-life. Therefore, we can use other models to demonstrate to students other lengths of half-life. The decay cubes, or dice, can work in exactly the same way as the skittles in our previous model. Students are provided a sample and given the conditions for decay. Our decay cubes here have 3 red sides, 2 green and 1 yellow. We can say to the students that each cube represents a nucleus in our sample, and that if it lands red face up, it has decayed. We then repeat the roll and remove process that we discussed in the skittle model, and each time we remove the decayed blocks, we build our column for our graph, or jot down the numbers to graph as we go along. Again, at this point we should consider the number of blocks we use in our model. With 30 across the classroom, students will get data that gives them the idea of exponential decay. However, there will be data points that do seem anomalous. With 100 blocks, the data looks smoother and closer to that of a true exponential. With these models, we have to weigh up the result we want the students to see and the feasibility in our own classrooms. The major benefit of this model is that we can change the rate of decay by changing the probability that any individual nucleus will decay. Experimenting with the red sides of our cube gives us a 50% chance of decay, which will give us a curve similar to that in the skittle model. However, if we use the green sides to denote decay, then we will have a slower rate of decay. Each roll allows each nucleus a 33% chance of decay. We can change this again by selecting the yellow side to represent the decay, reducing the probability of an individual nucleus decaying again, and slowing the rate of decay. This is also easily done with dice. As the teacher, you can allocate the numbers that means the nucleus has decayed. When using dice with a class, each student could roll 1 die and the data can be collected by the teacher straight into an Excel chart like the one shown here. Students declare themselves decayed when they roll the number indicated by the teacher. Depending on what you're trying to demonstrate, this could be matching one number, odds or evens, or even a random pairing of numbers, in order to show different decay constants. As the students' dice decay, we enter the numbers remaining into the spreadsheet and watch as a best fit exponential curve is plotted. We can then identify with students the half-life of our dice by drawing lines from the y-axis at the point representing half the active nuclei have decayed, to the exponential curve, and down to the x-axis where we can read the number of rolls. We can repeat this process for the next half-life as well, showing that the time taken to reduce the remaining nuclei by half is always the same. In this case here, it's approximately 2.9 rolls. In summary then, dice or blocks with different colour sides can be used to model the random decay of nuclei with the roll and remove method described with the previous Skittles model. We can model different decay constants and rates of decay by determining which colour or which numbers on the die represent the decayed nuclei. Decayed nuclei can be gathered into columns, as with Skittles, for a qualitative way of looking at the relationship, but can also be collected as data live with the students and plotted onto a graph. This way, students can read the half-life from the axes. It's also important to remember that number of roles is our unit of time in these models, and that this is how we can express the different half-life values. Being able to demonstrate different decay curves should help with avoiding the misconception that every role is a half-life. Measuring the half-life of a real radioactive isotope brings some of the excitement of radioactive decay into the school laboratory. Students can observe as one element decays into another and can measure the decrease in activity as the number of active nuclei decreases. A demonstration can be done with a protactinium generator to show the exponential decay of protactinium-234, a granddaughter nuclei of uranium. It has a half-life of just over a minute, which gives students a chance to measure and analyse the decay in a single lesson. Let's take a look back on an example of how this is actually used in a lab.
We're going to use the protactinium generator as a radioactive source with a short half-life. It's stored upside down, attached to the inside of the lid. The way the protactinium generator works is that there's a mixture of chemicals inside, and when we shake them, the isotope with the shorter half-life comes to the top and is able to be measured by the Geiger-Müller tube. And we've now got to give it 20 seconds to settle inside the container. And what I need to do is to record the count rate every 10 seconds over 5 or 6 minutes. Reset the timer, and I'm going to write down the count rate every 10 seconds. And 10 seconds, 154. I've reset the counter. Okay, and what will happen is over the 5 or 6 minutes, that count rate for 10 seconds will decrease as the half-life of the radioactive isotope continues on its decay curve.
Another way to measure the decay rate is with a computer data logger, which will plot the results on a graph. The count rate will increase for the first few seconds, so we exclude those. You can highlight that the points don't make a smooth curve because of the random nature of decay, but drawing a smooth curve through the points shows the trend of the readings.
Once we have modelled decay with our students, we can then move on to comparing different isotopes that have different half-lives and considering what they may be used for in the real world. Here we have 3 decay curves plotted on the same axis in order to compare them. Decay 1 has a half-life which can be read from the graph of 1 day. It also has the steepest drop-off, meaning that in the shortest amount of time it will have very low numbers of active nuclei left. Decay 2 has a half-life of around 1.9 days, and Decay 3 has a half-life of 3 days. You can see with Decay 3 that it takes a much longer time for the number of active nuclei to reduce down to the levels that Decay 1 reached within the first 3 days. The steepness, or more appropriately the gradient of these decay curves, represents the activity of each isotope, as activity is defined as the average number of decays per second and can be calculated as the change in the number of remaining nuclei over the change in time. The steeper the line, the higher the activity, meaning the radioactive sample is decaying quickly. So, how is this information about different isotopes' decay curves useful? Well, one example is if you are having to store radioactive isotopes that were the waste products in nuclear power stations. These isotopes have a long half-life and therefore need to be stored carefully for thousands of years for the activity to fall to acceptable levels. This is a problem that needs to be considered by engineers and scientists. An example where a long half-life would be a positive feature of a radioactive isotope would be when designing unpiloted space missions that use a radioactive source as a power supply. Isotopes that have a short half-life are often used in diagnostic medicine. Here, they want a source where high activity to maximise the value of the procedure, but has a short half-life to reduce the patient's risk of long-term exposure to radiation. Thank you for watching this video today. I hope it's been useful in thinking about ways of modelling some of the trickier concepts in radioactive decay, and that there are some strategies and techniques that you'll take away and try in your own classrooms. Please take a look at the other videos in the series and keep an eye out for future content on spark.iop.org. Thank you.